So the difference between a strong acid and a weak acid is that a strong acid will ionize completely, where a weak acid does not ionize completely. The same thing is true for a base. So a strong base down here on the bottom right is ones where they ionize completely. So in other words, it goes from, say, OH minus all the way to O2 minus. So that's a strong base. Okay. Now what we'll notice that's interesting is that water is here twice. Water is both an acid on the left side and a base on the right side. And water is kind of the cutoff point between the different types. So like acids that are above this water part are strong, below it they're weak. Here the bases that are below water here are strong, including OH minus, including the water. Everything above that is a weak base. So this chart is a very handy way of remembering when something's going to be weak or strong, which allows us to tell whether the light bulb is going to light up a lot or a little bit. Okay. So related to this topic is something called net ionic equations. So when you do a reaction, say between hydrochloric acid, which is a strong acid, and sodium hydroxide, which is a strong base, because here we have, on this graph, let me clean it up a little bit. So HCl is right here at the top, and the other one said NaOH, but here's the OH, that's the base portion of it. So that means that OH minus is in the strong base area and HCl is in the strong acid area. So if I take those two and I react them together, it's what we called a double displacement before, or replacement, depending on, they mean the same thing. So a double displacement is where we switch the cations in the reaction. So the cation here in HCl is H plus, and in the other compound, sodium hydroxide, it's Na. It's Na plus. So what we're going to do is we're going to just take the H and pair it with the rest of this hydroxide. So you get an H plus OH, and that is water, H2O. That leaves behind the other cation, Na, with Cl. So that leads to salt. As it turns out, whenever you react an acid and a base, you always get a salt of some kind, not necessarily NaCl, but that's possible. And you get a water. So that's an important fact to remember. Okay, so for writing the net ionic equation, what we do is we ask ourselves the question, okay, if these are strong acids or strong bases, we ionize them. So the question is HCl strong or weak? And the answer is that it's strong. So we would write it how it actually exists when we have HCl solution. Remember that these are aqueous because acids and bases always are. So we would, instead of writing it as HCl, which we know isn't really how it's existing in the solution, we write it as H plus and Cl minus. Same thing for, so sodium hydroxide is a strong base, so therefore it actually exists as sodium ion and hydroxide ion. And then NaCl is an ionic compound, so that means that when it's dissolved in water, it would actually be present in the form of sodium ion and chlorine ion. Now, so that symbol would be AQ after it because it's dissolved in water. H2O would not be written as AQ though because, water dissolved in water just feels weird. So instead we write that as liquid in our reaction. And the sodium hydroxide is also AQ because it's a base. So what this tells us is if a substance is not aqueous, then we would not ionize it. So water stays as water. Now, to figure out the net ionic equation, net means like after removing things. So like your net income is after they take out taxes. So what we're going to do here is, now that we have a complete ionic formula, everything that exists as ions is written as ions, and everything that exists as a molecule is written as a molecule. So the net is what you get when we cancel things that exist on both sides. So we notice there's an Na plus on the reactant side and the product side. So we get to cancel them out. They don't change. They're the same in the beginning and the end. So we're just going to cross them off. The same thing is true for chloride. So that means that the net ionic equation for this acid-base neutralization is what happens when you take H plus and OH minus, and it forms water. This is true for all acid-base reactions. So this tells us that any time you're doing acid-base reactions, the Na plus, the conjugate, doesn't matter. The chlorine doesn't matter. So it could be anything, and you're going to get the same result. You always get a reaction that forms water. Okay. So here's some practice. All right, so what is the net ionic equation for the reaction between sodium phosphate? Okay, so we have to translate that into a chemical formula. I know that sodium is Na, and phosphate is a special group that's on the back of the periodic table. So we pull out the green periodic table, flip it over, and look for the word phosphate. And what we find is that it says that it's PO4, and it says that it has a 3- charge. That's really important because I have to balance the charges in my compound before I can get any kind of reaction out of this. So if phosphate is a 3- charge, and then I look at the other side, the front side of the periodic table to find out what sodium is, it's in group 1, so it always loses 1 electron to become +1. These don't balance right now. I need to have the same number of pluses as I do minuses. So in order to make that happen, I have to have 3 sodium. So it's +1 times 3 gives us +3. Okay, so now these balance out. So the compound sodium phosphate is 3 sodiums and 1 phosphate. If this is not familiar to you, then you need to review nomenclature, which is naming. I have a series of videos available for that if you need help. But also it's in your textbook. All right, so we have sodium phosphate, and then it says solution. Solution means that the symbol after that is AQ. Then it says we're also reacting it with calcium chloride. So the symbol for calcium is Ca. The symbol for chlorine is Cl. And calcium is in group 2, so it wants to lose 2 electrons. Chlorine is in group 17, so that means that it wants to gain 1 electron, so it becomes -1. These don't balance, so if I want to have the same number of pluses and minuses, I have to multiply the -1 by 2 so that we get a -2. That means I need to write CaCl2. Okay, and then lastly it says here AQ for that one. Okay, I'm just going to rewrite this to be a little bit neater so I have more room. All right, so I have 2 ionic substances that are getting mixed together. And so even though these are not acids and bases, these are ionic compounds, the same kind of reaction applies. This is a double displacement reaction because I have 2 compounds to begin with. And so the cations on each side switch places. So Na is a cation and calcium is a cation. So in the products here, we're going to end up with Na paired with the partner that was on calcium. So calcium has chlorine with it, so we're making sodium chloride. I know that has a +1 and a -1 charge, so I only need to have one of those each to make the compound legitimate. I am not going to worry about the fact that I have 3 sodiums right now. First, I have to tell what the products are, and then I will worry about balancing atoms. Okay, so we balance the charges and then worry about atoms later. So my charge balance is there. Oh, and this is probably going to be aqueous because the other solutions were aqueous. So I want to include that as well. And then, let's see, calcium. I'm out of space, so I'm going to come down here. So calcium is going to get paired up with the anion from the original, the sodium compound. So that means calcium and phosphate are going to pair up. We said that phosphate has a -3 charge and calcium has a +2 charge. So those are not balanced. This one's a little bit more tricky because I can't just multiply one of them to get the right balance here. What I need to do is multiply both of them to get a common factor. So if I go +2 times 3, that'll be 6 pluses. And if I go -3 times 2, we get a -6. So those balance each other out. So that means that I need to have 2 phosphates, which I'm going to put it in parentheses because otherwise, like if I don't, then it just looks like PO4 2. So you got like 42 oxygens on there, which is crazy. So I'm going to put brackets around phosphate. And then the calcium we said needs to be multiplied by 3. So I'm going to put a 3 after the calcium. I don't need brackets there because it's just a single atom. Okay, so our final reaction looks like this. All right, so we've figured out all of the reactants and products. My charge is all balanced, so everybody's happy. Okay, now I'm going to deal with the fact that I have 3 sodiums over here and just 1 here. And I'm going to do that by changing the coefficients, right? So it's a 2-step process. First, you figure out what your products are, and then you worry about balancing. Don't mix the 2 steps together, or else you're going to end up creating compounds that don't exist. Like, for example, Na3Cl is not a compound. It's impossible to have 3 sodium ions with 1 chlorine ion. Okay, so we're not going to do that. Okay, so now that I got my charges, I know everything that is a legitimate compound. Now I'm going to balance it by changing coefficients. So like sodium gets 3. I always like to look at the metals first because that actually makes the work a lot easier. I have 1 calcium on the left, but I have 3 on the right. So I'm going to fix that by adding a 3 there. Now I'm going to look at the not metals pieces. And so like phosphate has 2 over here, and I only have 1 on the left. So that means I have to make this a 2. And now that kind of sucks because I just messed up my sodium balance. We said we needed 3 sodiums, but if I have 2 of this entire thing, that means I have 2 times 3. So I got 6 sodium here in order to get my 2 phosphate. But that's easy to fix. I'll just go back over here and turn this into a 6 instead of a 3. Oh, and actually that was great because this means I have 6 chlorine atoms, and since 3 times 2 is 6, that makes the chlorine balance on both sides as well. So when I'm balancing reactions, I always do a little double check at the end, right? And so we're just gonna count them and make sure everything is good. So on this side we have 2 times 3 sodiums, so it's the coefficient of 2 times the subscript, so that equals 6 sodiums. I'm going to treat phosphate as one group because it doesn't break up. So we're going to go 2, this 2 applies to the phosphate and to the sodium. So there's 2 phosphate groups. If you want, you can also think of that as 2 phosphorus atoms and 8 oxygens. It doesn't matter, but I find it easier to think about it as a group. And then we have 3 calcium ions. So calcium is 3. And chlorine is 6 because it's 3 times 2. Over here we have 6 times 1 sodiums. So that checks out. Phosphate is right here. It's PO4, and there are 2 of them. So that's the same. Calcium has a subscript of 3, so that's also the same. And then finally chlorine is 6 times 1. So this reaction is balanced. So it's all finished. All right. So All right, so there we go.